Hello everyone, thank you for joining us today for Permanganate 101 webinar with our speaker, John Boll with Carus. I'm Ashley Clark, Marketing Specialist, also with Carus. A few housekeeping items before we get started. All attendees are in listen-only mode to help cut down on any background noise. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel or email us directly. If you submit questions through GoToWebinar, we will receive a report with the question and your contact information to follow up directly after the webinar. Here are a few ways to find us. We have listed our website and general sales and marketing email address, as well as my email address. Do you receive our email blast for upcoming webinars, presentations, trade shows, and technical information on our various solutions? If not, sign up on our website. You can find the Join Our Email list on any landing page on the right-hand side. Be sure to select the industry when signing up to ensure you receive the most targeted information for your needs. And we can't forget to mention our social media platforms. We encourage you to connect with our Carus page as well as our team members on LinkedIn, where we are often sharing upcoming events, including webinars, industry articles or news, sharing relevant posts from other industry experts, and more. Listed here are links you can visit for upcoming webinars and also our website. At this time, I would like to take the opportunity to introduce our speaker, Mr. John Boll. John is the Global Technical Program Manager for Carus. He has been with Carus for over 45 years, serving in a variety of sales and marketing positions. The Technical Service Department provides chemistry and applications customer support, including on-site lab testing and plant-scale startup and troubleshooting services. John earned his Bachelor of Arts in Engineering from Purdue University. He is a member of the Water Environment Federation and the American Water Works Association, where he served as the AWWA Illinois Section Chair from 1992 to 1993.
This is, as Ashley was mentioning, I've spent an awful lot of time with Carus and talking about permanganate, so this is one of my favorite topics to talk about. Hopefully, as we go through the slides, you may have some questions, and as Ashley was saying, feel free to submit those on the chat line. I do have a sort of a plan or a route that I'm going to follow today that you can see on this slide. I'm going to talk a little bit about what commercial permanganate products are available now at this particular juncture, and then we'll talk a little bit about oxidation and permanganate chemistry. Not going too deep into the weeds on that one. And then we'll talk about application categories and different types of permanganate uses that we've looked at over the years and are currently being applied right now. So let's start with the permanganate products. Hopefully many of you are already familiar with how permanganate is packaged and delivered, but let me review that real quickly here. First of all, permanganate is available as a dry solid material. That's the Carus brand material that is potassium permanganate in its chemistry. It's available in different product grades, starting with technical grade, and probably the most popular grade is the free-flowing grade. They're essentially the same product, except that free-flowing has a desiccant that's blended into it at about 1% concentration. So the product assays vary by about 1%, but the idea of blending in a desiccant is that you retard or you slow down any type of water absorption into the product from the humidity in the air, and that prevents it from caking or lumping when you're storing it for a long period of time as a dry crystalline material, especially if you're storing it in a silo or in some type of hopper that feeds a dry chemical feeder. In addition to those two popular grades, we have permanganates that are 99% pure, and those are the pharma grade materials which conform to the US Pharmacopoeia, and also ACS reagent grade, which is the type of permanganate that is typically packaged in small 1 or 5 pound jars and is used in laboratories for reagent use. The dry permanganate comes in a packaged sealed container and is quite stable over a long period of time in that sealed container. Now, there are some special types, physical sizes of dry permanganates that are also packaged and delivered. Here you can see a reference to permanganate nuggets, which are slightly less pure than the other products, but you can see they come in rather large, chunky types of crystal sizes. That allows them to be used especially for broadcasting into water ponds or lagoons where they can sink slowly to the bottom through the water column. And also, if you're outdoors doing this, they are less dusty than some of the finer powdery types of technical or free-flowing grade materials. We also now are producing slow release or controlled release permanganate tablets. These dissolve very slowly when they're immersed in a flowing water stream and provide a relatively constant dosage depending on the flow rate of the water. They're really used for locations where it's not possible to set up a dry chemical feed system or a liquid feed system of any type, maybe because there's no electricity available or no mixing water available at that site, or a site that might be submerged in some way, and they're quite popular on the wastewater treatment applications. In addition to the dry crystalline products, there are pre-mixed concentrated liquids that are available under the Carus brand name. And there are really two grades of material that we supply currently. One is 20% active ingredient. It's called Carus liquid permanganate. And the second is a 40% active ingredient called Carus C, or concentrated liquid permanganate. And it is available in a variety of different sealed package container sizes. So what is permanganate? The potassium permanganate chemical formula is KMnO4, and the liquid permanganate products are sodium permanganate, whose chemical formula is NaMnO4. As I mentioned earlier, it's a stable oxidizing agent, which means we can produce it and package it and deliver it as a dry powder or as a concentrated liquid. And it can be stored and delivered to the end user and stored there for quite a long period of time. It has a shelf life that is really greater than a year. Also, because it's stable, it's pretty inherently safe to have around, especially if it's in its closed container. There are some specific recommendations for storing these materials, but there are no decomposition products, no degassing that occurs with these products. So they're very, very easy to use and to store. These products are manufactured in our plant in LaSalle, Illinois, and they're basically, we receive manganese oxide ore, which is mined out of the ground, and then we react it in a large reactor where we use oxygen and also some electricity to increase its oxidation state from 4 to 7. And when we get to 7, we are at the permanganate state. And when the customer uses permanganate, they are simply taking that oxygen and that energy back out again and returning the permanganate down to its manganese oxide ore state again. Now let me focus a little bit on permanganate chemistry. First of all, I put permanganate really into two buckets, which make it easy to identify. First of all, permanganate is a manganese compound. I bring that up primarily because it's very easy to confuse manganese and magnesium, which are really two different types of elements. So remember that permanganate as a manganese compound is a transition metal, and it's in the periodic table right next to iron in that particular row. Now, permanganate is also an oxidizing agent. As I mentioned, when we manufacture it, we put some energy into the manganese, we add some oxygen to it, and it's that oxidizing nature that the customer is using when they use the product. Oxidizing chemistry really is not, shouldn't be a foreign topic to everybody. In the easiest explanation of what it is, I just refer to it as energized oxygen. And of course, that's something that we use pretty much every day. The reason for that is because we live and survive in an atmosphere that is a very high percentage of oxygen. So we are surrounded in the environment with different types of oxidation reactions that occur. Everybody should probably be familiar with just the rusting of iron metal, which is a reaction with the oxygen in the air and the iron metal itself to form the red iron oxides. That's a rather slow process, and it takes a long period of time to go to completion. There can be oxidizing reactions that take place that are very rapid and very fast, such as the burning of fuel. And they're fast enough and rapid enough that the exothermic nature of that reaction produces light and heat when it occurs. And the complete oxidation of organic materials, in this case a wooden match, will eventually end up as just carbon dioxide and water if the reaction goes to completion. Now, to the chemists, oxidation and reduction reactions really have to do with the transfer of electrons from one compound into another. And that's a little bit more formal explanation of what it is, but the transition metals such as manganese and such as iron are really good at giving up or accepting electrons in different types of reactions that they might be involved in. Here's an example of the oxidation of dissolved manganese using potassium permanganate as the oxidizing agent. I see that my arrows have moved a little bit in this graph or this chart, so the arrows on the reaction side should really be pointing to the MnO2 molecule that's occurring there. So you have oxidation and reduction occurring always as a pair. They never occur just one by themselves or the other. Here's an example of an oxidation reaction that we would typically have with an organic molecule in most of the environmental oxidation reactions that we're doing. I mentioned earlier that a complete oxidation reaction with an organic material would go to carbon dioxide and water. In the environment, that typically never really happens because the conditions that we're following aren't rigorous enough to drive it to that endpoint. So typically what you have is the oxidation of an organic molecule where you're fragmenting it and making a big molecule and turning it into smaller molecules. In the case of permanganate, organic acids are a very common byproduct or end product for that partial oxidation reaction. So permanganate likes to react with organic compounds, and in particular, it likes to react with specific functional groups on those organic molecules. And here you see a diagram of some of those types of compounds that we like to react with. Certainly alkenes and alkynes, which are double bonds and triple bonds, are one of the very first things that permanganate reacts with and reacts with very readily and very quickly. So we can break apart different types of organic molecules by reacting at those particular sites. We may also react with alcohol groups or the sulfur equivalent of an alcohol group, which would be a mercaptan. You can react with some aromatic groups, especially if there are electron withdrawing functional groups on the ring. So the case of phenol that you can see in the lower left-hand portion of the diagram reacts very, very quickly with permanganate. You can react with alcohols, aldehydes, ketones, and esters very, very nicely with permanganate as well. And then the nitrogen equivalent of kind of an alcohol group, which would be an amine groups on an organic molecule, react very nicely with permanganate too. In most reactions that you deal with in chemistry, the pH conditions will affect the reaction speed and in some cases what the endpoints are. In the case of permanganate, we don't really worry too much about the pH of the reaction because most of our reactions occur in the pH range of 3 to 12. And in those cases, we're going to accept 3 electrons on the permanganate, and we're going to produce that MnO2 solid material, the manganese oxide, that is familiar in most permanganate oxidation reactions. There are some differences that occur if the system is extremely acidic. So here I'm showing that as less than pH 3, where you may have a complete 5 electron transfer occur. Or when the alkalinity is very high, that I'm showing here as greater than pH 12, where you can lose or accept 1 electron and go from permanganate to manganate species very, very easily. But those 2 extreme conditions are very rare in most of the applications that we'll be talking about today. Now let me talk a little bit about oxidation chemistry in general. It's really kind of a fun chemistry. It's a chemistry that you can read about in the chemistry textbooks, especially organic chemistry textbooks, because most chemists are interested in using oxidation chemistry to build or synthesize some type of particular end product that they need as an active ingredient or as some type of useful organic that can be used in a different kind of application. That's a little bit different than a lot of the applications that we deal with on a daily basis, which are those on the right-hand side of this screen, which talk about breaking something down or destroying it or purifying it. So we're going in sort of the opposite direction. We're taking large molecules and making them into smaller ones. I like to put commercial oxidation reactions into one of 4 large buckets. Most oxidizing agents fall into these types of categories, starting with the upper left-hand corner box here, which are the synthesis reactions that I just referred to, or the chemical purification reactions, or sometimes surface cleaning, such as cleaning metal rod or wire, I put into this particular category as well. In the upper right-hand quadrant, you can see that bleaching is a very common application for different types of oxidizing agents, and permanganate can be included in this particular category as well. If you think about chlorine bleach or hypochlorite bleach, you can associate oxidation chemistry with bleaching very, very easily. In the lower left-hand quadrant, you can see that oxidizing agents are typically some type of biocide. They are disinfectants, and they have many medicinal and veterinary uses. They're therapeutic in many cases. In the case of permanganate, from Carus, none of our products are registered with the EPA or with the FDA as biocides, so we're not allowed to sell or promote permanganate for any type of end-use application that would fall into the category of being a biocide. The final quadrant on this screen is the lower right-hand side, which is what I term the environmental reactions, and those are really what we're going to be talking about today for the most part, and these are really the applications where we're talking about drinking water purification, wastewater treatment, soil remediation, or in some cases even air pollution control. So let me talk a little bit about several of those environmental applications. First of all, they're the applications where we're treating a contaminated soil to remove very specific types of impurities that might have been disposed of improperly there in the soil. If you want to reuse and build on this particular site, it's necessary to go in and remediate it in a relatively short-term type of application. And here permanganate is used quite often, in particular to remove or destroy trichloroethylene or perchloroethylene, which are used as cleaning solvents in a lot of cases, and have seeped into the ground and can contaminate groundwater supplies. In some cases, the contamination can be deep underground, so the permanganate is actually injected through different types of wells that are inserted into the site. And sometimes the contamination is relatively close to the surface, where the permanganate can just be mixed in to the soil and allowed to react very, very quickly there. Of course, permanganate has a long history, really about 100 years of history of being used to purify our drinking water supplies. There's several things to know about that. First of all, permanganate is used both with surface water supplies and with groundwater supplies. And of course, you can really categorize the contamination into one of two categories. Those are inorganic, natural, or man-made species. And in that category, you have metals in particular, such as iron and manganese, that can appear in either surface waters or groundwater supplies. Certainly sulfide material can be quite common in these supplies as well and can be found in either one of them. In groundwater supplies, we also run into a couple of different types of contamination. We can run into radium, which is a naturally occurring material. There's no real oxidation reaction that takes place, but the radium is absorbed onto the manganese oxides that are produced from permanganate reactions and can be removed when those manganese oxides are filtered out of the system. In the case of arsenic, we're really talking about an oxidation reaction from arsenic 3 to arsenic 5, and then arsenic 5 can be absorbed onto metal oxides as well. Either iron oxides or manganese oxides work very, very well for arsenic absorption. Many of the permanganate water treatment, drinking water treatment applications have to do, of course, with natural or man-made organic materials that might be in the water. Again, in the surface water supplies, you have much more different types of naturally occurring organic material that might be there. And that organic material might show up as either a taste, an off taste, or a bad odor associated with that compound. The organics may be a precursor material to forming disinfection byproducts when we chlorinate the water. And removing those with permanganate is a way to control those disinfection byproducts. There now is a big research effort into organic materials released by blue-green algae and appear as algal toxins in the water supply, which can be detrimental to human health or animal health. Organic material in surface waters might show up as color. So here you might say, in this case, we're bleaching the color out of the water by adding an oxidizing agent such as permanganate. And then just organics in general, which are lumped together into large categories such as total organic carbon, or dissolved organic matter, or natural organic material, covers a wide variety of different organic type of products that might be present. It is possible to see organics in groundwater supplies, especially if the wells are not particularly deep, and so they can be contaminated from the surface. But you can see color in groundwater. In the state of Florida, for instance, which of course is very highly swampy kinds of water on the surface, that swamp water can be actually picked up in wells and is a very high color background associated with it. So why is it important to think about the permanganate reactions and the functional groups that might be on an organic molecule? Well, it turns out that those functional groups and the structure of that organic molecule are what contributes to its characteristic taste or odor. If it's volatile and it's released from the water supply, our noses are quite good at monitoring these organic molecules and detecting them as some type of characteristic odor. And If we can, through oxidation treatment, attack or destroy those particular functional groups, it's possible then to get rid of the characteristic taste or the characteristic odor. So in the case of permanganate, we're looking to react with the double bonds or triple bonds on those structures, or the functional groups such as the alcohol groups that might be present there. And there's another double bond that we might attack. And by breaking those organic materials down, our goal is to make them tasteless or odorless. Now let me concentrate very immediately here on inorganic compounds, because they're very, very easy to follow. There aren't that many oxidation reactions that we use on a daily basis to remove inorganics from water. The two most common ones are the removal of manganese or the removal of iron from water supplies. And we do that simply by, excuse me, taking the dissolved ionic species, manganese 2 or iron 2, and converting them through oxidation chemistry to their byproducts that precipitate out as solids. And then our water treatment systems, especially our filters, can remove those solids and remove them from the water supply. I mentioned earlier the oxidation of arsenic 3 to arsenic 5. It would still remain in the water if we didn't absorb it onto some type of solid material and then remove that solid material out. In this case, we're showing arsenic 5 being produced from the oxidation chemistry, and then it would absorb onto that MnO2 or manganese oxide block that forms during the oxidation reaction. Hydrogen sulfide is removed by oxidation chemistry, and we go in a complete oxidation reaction from sulfide to sulfates. But there are many different byproducts of sulfide oxidation that can occur, everything from sulfur to sulfites to all the way to sulfates. The oxidation of soluble manganese is very well known when we use permanganate to do it. In fact, if you look at any textbooks, or if you travel globally and you talk to people about water treatment with permanganate, almost everybody will recognize that permanganate can be used to remove soluble manganese from water supplies. It's a very efficient way of doing it because you have two manganese compounds reacting together. So you form a large amount of MnO2 solids, and you can use those solids in a variety of different beneficial ways. One of the ways that we do that is, as I mentioned, by absorbing radium from groundwater supplies onto those manganese oxides. This was a reaction and a application that was investigated at the University of Iowa and has been instituted and applied now on full-scale systems. In this particular case, we don't need the permanganate because there's no reaction with the radium there, but we do need the permanganate to react with manganese salts to produce the freshly precipitated manganese oxides that are used to absorb the radium out of the system. Typically, these systems are groundwater supplies, so they have some type of pressure filter system associated with them. And there you can see a tank of the brown or black looking manganese oxides that we've produced. And those are injected directly into the water supply to do the absorption. So in surface water supplies, we know that one of the contaminants that we can run into is biological in nature, and that's blue-green algae or cyanobacteria. The water industry has known about cyanobacteria for really decades, and they know it because it can grow in very, very high concentrations, and in fact create what are now referred to as HABs or hazardous algal blooms. We know what algae can do to a water system, right? It can, because of the high biomass, it can cause clogging of intake screens. It increases the requirements for coagulants because of all the biomass that's coming into a plant. If we're carrying it all the way to the filters, it can create short filter runs and increase backwash requirements. It of course increases the demand for chlorine, and in doing that, it creates a lot of disinfection byproducts in reacting with the chlorine. We've known for a long time that they can produce compounds that create unpleasant tastes and odors in the water. And now, of course, we know that they can produce different types of algal toxins as well. So we're looking at all of these as organic materials and how can we control them, and how can oxidation chemistry help to control them. So here are a lot of very classic types of algae species that have been identified. Initially, when we would think about them in terms of taste and odor compounds that they're producing, we would identify them by their characteristic and put them into different types of descriptor types of categories, so that we could talk about the byproducts and how the byproducts impact the water supply. So we would describe the characteristic as maybe being grassy or medicinal or fishy or musty, earthy in nature, or flowery. And this was before we maybe had the analytical capabilities of identifying specifically what the compound was that would be giving us those types of characteristics. So we would use odor panels and people's noses, right, to identify the intensity of that odor associated with water, and that panel would characterize what the odor was that they were smelling. Now we know with our analytical techniques that we can identify specific compounds. We know what their structures are. In the very right-hand column, you can see our normal suspects that we've known for years and know that they create problems in waters, but now we also know that these particular species will produce different types of cyanotoxins. Probably the most prevalent toxin are the microcystins and the antitoxin A's that we can identify in water supplies now. And you can see from this chart how they are toxic to different target organs within our systems. Now, I wish there was a silver bullet for all of these different types of algal toxins that have been identified. And here are the 4 primary ones at this point. You can see that permanganate reacts with the microcystins and the antitoxins, but not with the cylindrospermopsins or the saxitoxins. Chlorine, and in this case, this is free chlorine, so under slightly acidic conditions, chlorine is quite good, although it doesn't react with the antitoxin. Chloramines don't do very well with any of them. Ozone, of course, being a very strong oxidizing agent, reacts with 3 of the 4. And chlorine dioxide at this point has not been identified as reacting with any of these. As is typical with organics in water supply, you also have the techniques of using carbon, for instance, powdered activated carbon or granular activated carbon for absorbing these materials out of the water supply. Different types of filtration membranes remove these products. If these cyanotoxins are part of the bacterial cell, still their blue-green algae cell, then coagulation, flocculation, and filtration will likely capture a lot of them as well. But again, there is no silver bullet, and what we rely on in the water industry is a multi-phase approach or a multi-stage approach to removing any of these particular types of contaminants that we might find in a raw water supply. So where is permanganate used in a drinking water supply? It's usually added as one of the very first chemicals in the treatment process, usually directly to the raw water supply itself. Why is it used early in the treatment process? Well, there are really 3 or 4 particular reasons. First of all, as you've seen from some of the pictures that I've been showing today, when you put permanganate into water, you have a very characteristic pink or purple color that is formed from the mixing of permanganate and the dissolving of permanganate in the water. Well, we want that pink or purple color to go away early in the process. So we want the reactions to take place early, and we need a little bit of time for those reactions to take place. So if permanganate can be the first item that goes in, that usually provides us with some time before the flocculators or before the rapid mix even, where our coagulants are added. Remember, when permanganate reacts, It precipitates out as a manganese oxide flock material. So we want to be able to capture that material and settle it out in the water treatment process, or at least filter it out in the water treatment process. So we would like to have all that MnO2 formed at the point of coagulant addition, which is typically at the rapid mix. If we can't get it formed that early, it can still be removed in the flocculation zone pretty typically, so that we can take advantage of the time in that flocculation zone as well. But we try not to carry it too far into the sedimentation basin because we do want it to grow in size and we want it to settle out before we get to the filters. The other reason we try and get permanganate in early in the process is there are some other interactions that can take place. At one time, permanganate would react with some of the polymers that were used in water systems. The polymers these days are pretty resistant to oxidation chemistry. So that's not as big an issue as it used to be in the past. But permanganate will react with powdered activated carbon. So if carbon is being applied into the system, and typically it might be applied at the rapid mix, we don't want to lose our permanganate by reacting it with the carbon. So we would put permanganate in first, allow it to react, and then follow it with the carbon at a later point in time. In groundwater systems, I mentioned typically what you will see is a pressure filter of some type. Now, because in groundwater supplies, what we're usually trying to remove are sulfides or dissolved iron or dissolved manganese, the advantage we have is that those reactions are very, very rapid. They go within a matter of minutes. And so the short period of time in the pipeline ahead of the filter and the headspace in the filter itself provides us with more than enough time for those reactions to go to completion. In some cases, the pressure filters use special sand in them that is referred to as green sand or manganese treated green sand. And that sand is also an oxidation chemistry and can remove some iron and some manganese on its own as well. But typically, permanganate is fed continuously ahead of a green sand filter so that you have the combination treatment of the permanganate and the sand itself for removing those particular types of compounds. Now I'm going to switch over to the wastewater side of applications. Here, typically what we're talking about is odor control with permanganate. And most of the odor compounds that we run into are different types of sulfur compounds. So different kinds of mercaptans, and including hydrogen sulfide itself, which is typically in the highest concentration in the air and wastewater treatment. You'll notice in this graph that they have characteristic odors that can be associated with them, but also that their thresholds, or where the concentration in the air that our nose begins to pick them up, are very, very low. So when you're doing odor control treatment, you have to be very efficient and get those volatile organic materials down to very, very low levels. They are released wherever you have turbulence being created in a wastewater system, because the turbulence allows that volatile material to leave the water and go into the atmosphere. The application treatment points for permanganate will almost be always categorized by where in the system we're talking about the odor occurring. So there can be permanganate systems that are used at the treatment plant site itself, especially at the headworks where the collected wastewater first enters the treatment process. We use permanganate quite often in the biosolids dewatering systems, where these mechanical devices strip the hydrogen sulfide or the odors out of the sludges and into the room where the dewatering device is located. Permanganate reacts very, very quickly, so it can be injected just a matter of minutes ahead of these devices. And in some cases, permanganate is used where sludge is still just dewatered by using drying beds where the water is allowed to evaporate away. But initially, they can be quite odorous, at least until a crust is formed, a dry crust is formed on the top of these beds. So initially, permanganate can be sprayed on these beds as well to control the odors. Permanganate is used in collection systems, typically at lift stations or where gravity force mains meet gravity interceptors, and there's turbulence created and odors are released. Permanganate, again, is used very close to where the odor source is occurring because the reaction proceeds rapidly and to completion in a very short period of time. The one thing you do not get with permanganate, typically in collection systems,
John, it looks like we lost audio on your side. John, are you maybe muted on your end?
no, it should be open. Can you hear me?
I can hear you now.
Okay, good.
Thank you.
So we were talking about wastewater treatment, and in particular, we were talking about collection systems, and collection systems can introduce some hurdles as to how to apply a chemical product like permanganate and do the odor control you're trying to achieve. So the use of the controlled release tablets was really designed for these sort of locations where you can't set up a chemical feed system very easily, and you rely on the flow of the wastewater to dissolve the permanganate slowly and control the odor compounds, in particular sulfides, that might be present. Don't forget that we're not only talking about municipal wastewater treatment, but we may be talking about industrial wastewater as well. There are a lot of cases of industrial treatment where they're using lagoons for really collecting and equalizing wastewater flow rates. Sometimes these lagoons are aerated. Those are perfect locations for adding permanganate because freshly precipitated MnO2 and aeration work together in sort of a catalytic fashion to get rid of sulfide materials in particular. And we've even gone to rather exotic ways of applying permanganate by actually applying it from boats. One of the areas on the industrial side that we've worked with quite a bit over the last 2 or 3 years is really at landfills where they're collecting leachate that's coming off of open cells, and the rainwater that might occur is percolating down through this waste, and then it's collected and can have a lot of odorous components that are associated with it, not the least of which is hydrogen sulfide. Sometimes these systems are connected directly to a local sanitary sewer system, and they can be creating odor problems for that sanitary sewer system. And sometimes they're not close enough to be connected by pipeline, but they have to be connected by collecting the wastewater and then trucking it to a disposal site. At the disposal site, there can be a lot of odor released, but the permanganate can be added to the truck to destroy those odor compounds on the way to the disposal site. We have mining applications where the chemistry is not really unusual. In this case, we're talking a lot about iron and manganese precipitation, but just the application point is different because this is acidic leachate that is coming off of a mining operation, and it's dissolving metals out of the soils and getting them into the water supply. So these systems often involve pH adjustment to neutral pH and then oxidation with permanganate to remove the iron and manganese. Don't forget that odors can be associated with animal confinement operations as well, in particular with the spreading of animal manures, and permanganate has been used successfully in these types of applications as well. Now, there are a lot of industrial applications. Remember, our bucket's beyond just the environmental applications. So let me say a little bit about some of those. Permanganate is used in synthesis reactions. It was used quite extensively around the globe in the production of saccharin when it was used as an artificial sweetener. And there are a variety of other compound or organic materials that are produced using permanganate in an oxidation reaction in an intermediate step in producing those products. Permanganate is used to purify different materials such as zinc ores. Sometimes it is used to purify food grade CO2. And there were large applications for permanganate use in the purification of acetic acid. Permanganate is in fact sometimes used as a bleaching agent. It is used probably on the largest application in removing the blue aniline dye from denim to produce different kinds of washed out or faded out blue jeans for fashion, high-end fashion uses. Permanganate is also used to bleach kale and clay. It's used to bleach sponges and also beeswax that are used in candles. And it's also used to decolorize and bleach phosphoric acid. The aquaculture industry, where we're raising fish in ponds or in raceways, uses permanganate. It is used primarily for removal of unwanted tastes and odors due to organics. It can be used to destroy and remove a fish poison, which is referred to as rotenone. And it is sometimes used to control external parasites and bacteria on the surfaces of fish under special FDA regulations. Permanganate has been used to clean a variety of different surfaces. It is used to clean the surface of ferrous metals, in particular rod and wire, when that rod and wire is going to be coated in some way for decorative use or for specific industrial use, such as welding rods where they have to plate copper on the outside of the rod itself. Permanganate is used by the printed circuit board industry to clean the surface of the printed circuit board and prepare it for receiving copper plating, which is used to conduct electricity between the layers of different multi-layered circuit board circuits. And permanganate is used to clean equipment surfaces as well, everything from the hot sections of jet engines, where they can then be inspected during maintenance, to the insides of refinery equipment to remove pyrophoric iron sulfide in particular, and remove that scale from the inside of these processes so that they can go in and open them up and do maintenance on them. Permanganate is used a lot in the oil and gas industry at both refineries, where it is used, as I mentioned, to remove pyrophoric iron scale, It's used to treat phenol contamination in wastewater systems. It's used to control hydrogen sulfide in areas where you're dealing with high sulfur crudes, mercaptans, of course, or the organic sulfur equivalents, some cyanide oxidation, some iron oxidation and precipitation as well in the produced water in the oil fields where oil and gas are being produced. And selenium is one of those cations that can be absorbed onto freshly precipitated manganese oxides. So just to close out and to summarize very quickly here, permanganates are available in a variety of different product forms, different grades, and they can come in a variety of different package sizes. Permanganate is used in chemical synthesis and purification reactions. It is used in a variety of different bleaching applications. And of course, the largest uses of permanganate are really what I call environmental reactions, which include the drinking water purifications and the wastewater treatment and odor control applications. So with that, I'm going to turn it back over to Ashley if you're still there.
I am, yes. Thank you, John. All great information. If you do have a question, go ahead at this time and submit those. On this slide, it shows our sales managers' information and their contact info, so you can feel free to reach out to yours in your region. And then I'll have you do the last slide, John. Thank you. Shown here is our presenter, John's contact info, as well as our sales and marketing contact info. It looks like we don't have any questions that came in, so if you do have a question.
Ashley, I think the slides are available to the attendees, right?
Yes, we will have the slides and the recording that will be available on our website sometime next week probably, so feel free to share that within your network. Other than that, That's it. So have a great day, everyone.